We have come to the last wave transformation phenomena known as wave reflection. We have mentioned about wave reflection previously when we talk about the incidence wave that is being reflected by the barrier. Basically, an incident wave will be reflected by any obstruction, including the shoreline itself, and the reflection occurs at an angle which is the same as the incidence angle as shown on this figure over here. However, if we consider a wave front, multiple wave front that approaches a barrier and is reflected, then the wave reflection phenomena in front of a structure typically will have a patterns like this due to the superposition of the incoming and the outgoing wave patterns, the incidence and the reflected wave patterns, and this is known as Clapeyron-Goffler, which is a complex diamond pattern of island crests which move parallel to the boundary. This example of actual observation of these diamond-shaped patterns in front of a coastal structure. This figure here shows the effect of wave superposition. We have two different sets of wave here, and they are moving at a different speed. So as we can see, the result of these two waves when superimposed on one another produce this blue wave. We notice that the wave height of the superimposed wave actually changes with time, and it has a slightly different patterns or magnitude compared to the two original waves. We also notice that the vertical displacement of a water particle, for example this water particle, sometimes the vertical position is large and sometimes the vertical displacement is small. So when the vertical displacement is large, that is where the superposition of the two waves produce an antinode. But when the vertical displacement is small, like right now it's very small, is when the superposition of the two waves produce a node. If the two sets of waves are completely out of phase, which means that the phase angle of the incoming and the outgoing waves are different by 90 degrees, then we get a standing wave phenomena. Let's assume this is the coastal structure or the barrier, and we have an incoming wave moving towards this barrier, and as this incoming wave hit the barrier, it produces this outgoing wave, the reflected wave. And in this particular case, the incoming and outgoing waves are completely out of phase by 90 degrees. And as a result of that, the superposition of these two sets of waves produce this standing wave pattern. You notice that in this standing wave pattern, the wave basically just move up and down as if there's no propagation. If we look at individual point, for example, this point is a node where the vertical displacement is essentially zero in this case, and this remains as a node throughout. Whereas this point is an antinode, whereby the vertical displacement is the largest, and it remains as an antinode throughout. Now, assuming that there's no energy loss at this barrier, the incoming wave height and outgoing wave height is essentially the same, HR equals to HI. And due to this superposition of the two waves, then the standing wave here will now have a total wave height of 2HI. This figure here shows the animation of how a standing wave is formed in front of a barrier. In this case, the incoming wave and the outgoing wave are out of phase, and the standing wave is produced with fixed points of nodes and antinodes located at a distance of L over 2 from one another. So essentially what happened in a Clapeyron system is the incoming wave and the outgoing wave, which are oriented at an angle of alpha with the barrier, superimposed with one another such that it forms nodes and antinodes at different points in front of the structure. In the event that the Clapeyron systems form a standing wave, then we will be able to see a profile that looks like this, whereby nodes and antinodes are at fixed location, and the water particle motion beneath the water surface will be oriented in these directions, as shown in the next slide. Here, using fluorescent, we are able to observe how the water particles move in a standing wave underneath the antinode and also the node. However, in actual situation, it is unlikely that there is no energy dissipation on the surface of the structure. And so as a result of that, typically the reflected wave height will be less than the incidence wave height. So we have a reflection coefficient CR equals to HR over HI, which is typically less than 1. Now, since HR and HI are typically superimposed in front of the structure, it is actually impossible to measure what is HI and what is HR separately. If we try to perform a measurement in front of the structure, what we can get is the nodes and the antinodes. For example, if this is the wave structure, there is a set of incoming wave with a wave height of HI, and there's a set of outgoing wave with a wave height of HR. Due to the superposition of these two sets of wave, we are going to get an envelope which looks like this. If we move the measuring location, then we will be able to find a location whereby the vertical displacement is minimum, so that will be the node. And if we move the measuring location again, we will be able to find a location whereby the vertical displacement is the largest, and that is the antinode. So what we know is then a location where we get the antinode is a location whereby the incoming and the outgoing wave, the incident and the reflected wave, superimpose one another to produce the highest wave. It's a constructive superposition. They add on to one another. Whereas the node will be a location whereby there's a destructive superposition, so that the HI minus HR give us the minimum surface displacement. Of course, as we discussed previously, if there's no energy loss, then HR will be equals to HI, then the node will be equals to 0, and the antinode will becomes 2HI. But now we're talking about real situation where HR has a smaller value than the HI, so antinode is given by HI plus HR, whereas the node is given by HI minus HR. So it is possible for us to measure the antinode and the node. And if we obtain these two information, then we can use it to calculate the reflection coefficient, which is given by this expression over here. So reflection coefficient can be defined as the antinode minus the node divided by the antinode plus the node. examine this equation carefully, you will notice that the numerator on the top basically is hi minus hi cancel, and then we have hr minus negative hr, so we have 2hr on top. So we have hr on top. We have 2hr here. If we look at the denominator, we have hi plus hi, so we have 2hi, and then we have hr minus hr cancels off. So essentially this equation, if we simplify, we have 2hr over 2hi, which basically is hr hi. So basically is the definition of the reflection coefficient, which is the reflected wave height compared to the incidence wave height. But we use this form because we can only measure the antinode and the node. We cannot measure directly hr, we cannot measure directly hi. Now let's look at this example. Given the antinode and node of a wave envelope measures 3 meter and 1 meter respectively, determine the reflection coefficient. So here we have a situation whereby in front of the barrier or obstruction, we observe the Clapeyron's system. We try to measure the antinode and the node. We found out that the antinode equals to 3 meter and the node equals to 1 meter. So using the equation for reflection coefficient, we have antinode minus node over antinode plus node, so we get 0.5, so which means that our reflection coefficient is 0.5, which means that the reflected wave height is half of the incidence wave height. Before we end this lecture, we just want to highlight that the Clapeyron's system, which is also known as the short-crested wave, actually is responsible for the formation of vortices, which is going to be important part of the littoral transport and erosion of the shoreline. We will discuss more about the littoral processes, which means that the sediment, erosion and transport in the shoreline in our subsequent topic. Here, the incoming wave is reflected by the shoreline, and so it forms a type of Clapeyron's system. This progression of the wave towards the shore typically causes erosion, and this progression outwards of the shore typically is a backwash that carries the sediment away from the beach. And as a result of that, there is a net littoral drift, that means a net movement of sediment in this direction along the shoreline.